we'll transition over now to Engin. So I'll introduce, this is Dr. Kayraklioglu, who joined our team as a intern during his PhD program, and was recently, relatively recently, hired just before finishing his PhD at George Washington University. And so now he's going to present on some automated machine learning approaches for data locality optimizations in Chapel.
All right. Excuse me. Hello, everyone. You can see my screen share, all right? I'm hoping.
Yes, we can
without
see it.
any Zoom overlay. I never know what Zoom shows to you and what it shows to me. Anyways, so thanks for the kind introduction, Ben. My name is Engin. I'm a member of the Chapel team at HPE. But today I'll be talking about the work that I have done as part of my PhD before joining the Chapel team. And mainly I'll be talking about data locality optimizations. And the reason that we are having this focus is because they are really complicated, yet an important part of programming for HPC. The reason that they are complicated is even though we see them as a single thing that we do, it actually, a typical data locality optimization typically consists of many different subtasks, which rely on different system and application characteristics. So if you want to do some data locality optimization, I'll be mainly talking about communication aggregation or bulk communication, whatever you want to call it. You typically have to do many different tasks that rely on many different information that you have or you don't have about the system and the application. And if you look at the state of the art and see what we do in the field, we either rely on programmer doing everything. MPI falls into this category, or if you are really a savvy PGAS user, you're probably doing this, or you just rely on your language stack, your compiler, runtime, libraries, what have you, to do everything. But in practice, this is a really difficult task for language stack to automatically do. And I said this before, but I'll be mainly focusing on aggregated communication as a data locality optimization in this talk. There are many different other things, but I believe that's the most important thing, that gaps between, that is the gap between shared memory programming and distributed memory programming. So let's see some code and try to understand what the real issue is. So if you want to write a matrix transpose in Chapel, and you would write something like this, and clearly this is not just matrix transpose, this is a PRK transpose kernel, parallel research kernels. It's a suite of benchmarks. And what it does is in line 3 and 4, it does the matrix transposition. In 5 and 6, it updates the input and repeats it again. So if you have an application like this, you can write it this way and it would run really fine on shared memory. It will probably even scale with multiple threads. But if you want to go to distributed memory, what you would want is probably something more like this, where you have more code, you have more complicated code, not just more typing, but it's more thinking and more knowledge and expertise. And it also, maybe more importantly, you have a different application logic. So while I can read this unoptimized version pretty much in plain English and it will describe the algorithm well, things get really murky when you get to the optimized version. So here, PGAS nature of Chapel, of course, helps reduce the amount of code that you need to write, but still the way you think when you're writing this application is not much different than what a typical MPI programmer would do in terms of data movements. So in this talk, I will discuss 3 ideas to try to mitigate these. And these 3 ideas will be mainly a collaborative language feature for doing this data locality optimization, and a high-level profiler to analyze XCCs to distributed arrays, and finally a machine learning based approach that can automate pretty much everything. And while doing so, I'll put my focus on what they mean for a typical Chapel user, and I'll probably be, my talk will be probably very satisfying if you're expecting a lot of implementation details, experimental results, and things as such. But it's almost 3:30 Friday, so I hope that you are not expecting that. But I'll be happy to talk offline if you're interested. So let's talk about the first bullet, which is the collaborative language feature that we called locality-aware productive prefetching support, or LAPS. The motivation for LAPS is it is really hard for the compiler or the runtime system to do these kind of locality optimizations because of many reasons. Ultimately, it relies on, ultimately it's because it would rely on code analysis, either statically or dynamically, which is either difficult or too costly. So the question that we are asking here is, what if the user tells them, meaning compiler, runtime, or the language stack, exactly how the data is accessed, and let the language stack handle the nitty-gritty details of data movement, memory consistency, and such. And this work is published in ACM TACO in 2018. So let's go back to matrix transpose example. As I've shown before, this is your unoptimized example. This is your distributed memory optimized chapel code. So what we are proposing basically amounts to this. So what we have here is a single function call, or rather a method call in line 1 that tells the language stack basically that on distributed array A, we'll be doing some transpose operations. So why don't you just go ahead and prefetch the data to fit the transpose operation? The benefits are obvious if something like this would work. Code modifications are trivial, and more than that, application logic remains identical. So we basically have effective separation of concerns when it comes to application logic and application performance. So of course, transpose is a very simple example, and there are many other communication patterns in HPC. Here, we implemented 4 or 5 other different prefetch patterns. I show some of them here, but more importantly, we also implemented a custom prefetch pattern in which the user can give basically a lookup table, and the language system will still handle the data movement under the hood. Of course, it's much more difficult than just having a method call, but it still achieves the same separation of concerns, which will come in handy in few slides. So I'll summarize the experiments without showing real plots to keep things smooth. So we performed synthetic and application benchmarks and observed good, strong, and weak scaling. We observed up to 2 orders of magnitude faster than unoptimized code, which shouldn't come as a surprise, because we are doing bulk communication instead of doing all that fine-grained communication. We mostly observed on-par performance with manually optimized applications, and we also measured the memory footprint and showed it to be very limited. So the next thing is, LAPS is good, but it still relies on programmers' understanding and ability to make the correct calls. So the next question that we ask is, can a high-level data-centric approach, or rather a profiler, help the programmer use LAPS or do manual optimizations? So for that, the work that we done for that is published in ACM Computing Frontiers in 2018, and it's called Access Pattern Analysis Tool, or APAT. APAT is a profiler that is high-level and data-centric, and what it does is basically it collects access indices to distributed arrays in order to help identify spatial access patterns. And APAT can be used standalone or with LAPS, if you will. It has command line interface and graphical user interface. Here I'm showing the graphical user interface. Let me see if I can get my fake laser pointer going. Okay. So on the right-hand side, you are seeing a graphical user interface screenshot. This is a screenshot from profiling HPCC ptrans, which is a matrix transpose with block cyclic distributed arrays. And here I'm showing a run with 4 locales that are represented with these large squares, 4 large ones. And inside each of these, you see blue rectangles that basically marks the area that is owned by that specific locale, and different shades of red that specifies which indices are accessed by that specific locale. So you can see, for example, locale 0 and locale 3 are accessing all the indices that they own locally, so they are never doing any remote access, whereas locale 1 and locale 2 are doing some remote accesses. So this is a helpful way to understand the access patterns without digging too much into the code, which can get really complicated in real world cases. So APAT is sort of a step towards making programmers' life easier, but it doesn't take it all the way, right? Because interpreting the output from APAT and using labs appropriately is still a significant amount of work, and it still requires significant amount of expertise in the field. So the next and final question that we ask is, can we automate this process by making an AI model learn this access patterns and optimize the application using labs? Because recall that labs separates application and performance concerns. So labs can just inject some calls basically without actually doing any code transformation and hopefully get the benefits out of it. And this final piece of work was published in CCGrid in 2018, and parts of it is under review at IEEE TPDS. So let's recall some of the code that we have seen before, nothing new here. You have your unoptimized and labs optimized versions of matrix transpose. So what we are proposing with this next level of optimizations is basically just replace the call to transpose prefetch with a pragma that just says, okay, in this next block that you have, please optimize the distributed array A. So the obvious benefit here being is that you no longer need to worry about the access pattern. You're just saying that, okay, this portion of the code is really performance critical for me. Please do something about it. So let's see how this works. Let's get the pointer thing going again. So on the left-hand side, you have your application code that is unoptimized, but has pragmas in it. And on the right-hand side, you have your existing CHIUW environment with lab support and APAT. So what happens here is when you give this code to the framework that we are proposing here, the first component that takes the code is a pragma parser, where the pragma that you added in front of a block is parsed. And as a result of this parsing, we generate two separate source codes. So we are not compiling anything yet. We are just changing the source code, basically just a text operation. So out of this operation, we come up with two different source code, or two different versions rather. One is to be used with APAT that includes some profiler calls appropriately for the pragmas that you injected. The other is one that uses some labs calls to basically optimize the data locality. So what happens next is this data collection engine, which received the profiling source code, compiles this code and executes it with different input sizes that is specified by the user using a script. So with this executions, what we do is, because it's profiling executable, profiling source code, every time you run, you generate some logs, and those logs are passed to APAT. And when APAT parses those logs, it generates some access pattern information, which is just a mathematical representation of which parts of arrays are accessed. And again, this is just a detail that I'm just glossing over. I can talk more about it. And then once data collection engine collects enough data to do a batch of training, it sends them to machine learning daemon, which is just a process that runs in the backend and waits for batches of vectors to train a machine learning model. And this wiggly cycle basically repeats perpetually until some stopping point. And in the end, we have a trained machine learning model, which you can bundle up and compile with the labs generated executable that will use this machine learning model. And in the end, you have an executable that have bulk communication. So to summarize, the results we saw on par performance with labs with this, and good scalability. And an important thing is portable optimization. You can basically run this framework and teach the neural network, or it's not neural network in the final design, but machine learning model on your laptop, but just run it on whatever distributed memory system that you have access to. So it's portable in that sense. You don't have to train in different machines. The memory footprint is minimal. I saw like O1 type of increase in memory over labs. And it requires very little performance programmer effort. An interesting anecdote is like it takes, for example, 30 minutes to do this training with starting from an optimized applications. I think it was for Lulesh or DJAM, I don't really remember. I had the shared memory application ready. I started this framework, went to get some lunch, and when I come back, it was running and scaling well on a machine, on a supercomputer. So it was really nice to see that anecdote. Okay, to summarize, I presented 3 different approaches very briefly and probably vaguely to help with data locality in HPC systems. The main goal being to bridge the gap between shared memory and distributed memory programming. Obviously, programmers still needs to be involved, but in a much less disruptive fashion. And most importantly, the separation of concerns are achieved to a good extent, I believe, to a great degree that one person, a domain scientist, can write their application without caring about performance or distributed memory, and another person can take that application and optimize it without really caring too much about application logic. I hope I didn't go over time, and that concludes my talk. Thank you very much.
Thank you very much, Engin. It's great work.
Thanks.
We'll take questions now. I know Brad mentioned he had a question.
I'm trying to get to my Q&A box view, so if you can speak up the questions, that would be really great.
There's nothing in it now. I had a really high-level question, but if anyone had a technical question, that might be more interesting. And if so, please type it into the Q&A tool or the chat window if not. My high-level question, let's go with Brian's question. So Brian's asking, to what degree or how much effort would this approach be to integrate it into the compiler?
So as it stands, or as it stood when I finished my PhD, the compiler parts of it was really minimal and for only doing some support. Specifically, I added a special type of pointer that is used to support this approach, and it was mostly runtime based, most of the logic that I had. I definitely don't want to preclude the possibility of compiler doing all sorts of analysis in the code statically and using this automatically. I really wish we could have that. But at the same time, the only thing that I can say is it's a really difficult task to do such kind of static analysis and have enough confidence to do code transformation. I'm not sure if that's a satisfying answer, but that's all I can say, I guess.
That question was kind of similar to mine, although I was going to ask, Elliot accused me of asking him a loaded question later on, or earlier, and I was going to ask a similarly loaded question. But somebody else has cut in as well. Tyler asked, can LLVM help with the effort that you were talking about, getting it into the compiler, doing the analysis and transformations?
At the current state of the CHIUW compiler and how it works, I believe that most of the information that we need to make that observation is gone when we go to the LLVM point. And at the same time, I'm not very knowledgeable with LLVM, and there may be some sort of hooks in the earlier stages of compilation that we can inject in our AST so that the LLVM backend can benefit from it. But yeah, my guess is the information that we need is way too high level to think about the backend compiler.
We have a question in chat, and I had a similar question for that. So this is from Akihiro, what kind of machine learning algorithm did you use here?
Yeah, that's a good question. I think you're still seeing my screen, right?
Yes.
I have lists of them. In fact, I'll just show the comparison table. Maybe, sorry. Maybe this will show things. So we tested with 6 different approaches. One of them was a neural network. And I'm not a neural network or machine learning expert, but it was mostly like what we have available, and we just write a script and tests everything exhaustively. And in the end, we adopted ElasticNet. It's a linear regression method. That's kind of, as far as I remember, it's kind of not prone to outliers that much, and showed real good performance overall, considering many different factors.
Okay, and a follow-up to that is let's see, and what if there's a false positive for this model? So what if the model assumes a specific access is local, but it's actually remote?
Yeah, for that, that definitely can happen. And that's kind of the beauty that you have with labs, if you will. Just let me go back to some of the code samples that I have shown before for labs. Here, for example, because we are not separating or we are not changing the application logic, you can have this transpose prefetch call here in line 1, but your application may not be doing transpose prefetch at all. So under the hood, every access to A is checked by the runtime to see whether that specific index was prefetched by labs or not. So to connect that question to the machine learning approach, if machine learning predicts or gives false positive or rather false negative, maybe. I don't know the way you look at it, I guess. Definitely that can happen, and it's probably happening in the tests, but the underlying labs implementation can take care of that and use fine-grained remote communication if that particular index was not prefetched.
Okay, and we have a question in the Q&A. So what is the viability of a machine learning approach when your application deals with something like a graph or a sparse matrix, where subsequent executions may be looking at entirely different access patterns?
Yeah, short answer, I don't have a good answer for that question. Slightly longer answer, and I've been thinking about this question a lot, at least during my PhD. And I was, just to speculate, I was hoping or assuming or being a little bit naive about it, that graph applications use graphs of different characteristics. If you're doing some social network, your graph will probably have some like cliques and things like that. Or if you are doing some engineering kind of sparse approach, for example, you will have more like diagonal sparse matrices and such. So I was still hoping that some sort of an online learning version of this work can be used in such cases where you can learn as you go and hope that your graph still has some sort of pattern and it can be learned by the machine learning model. But as I said, it's not a good answer, I know that.
Okay, and we could probably take this last question since we're over a little. Is the data access pattern known beforehand, compile time rather than runtime, for the compiler library to optimize data locality?
So with the machine learning model, no, there is no pattern that is passed to the compiler. So compiler is completely unaware of the access pattern, and it doesn't do much in terms of optimization. As I said, optimization is mostly runtime based. So yeah, there is not much compiler work as part of this.
Cool. Well, thank you very much, Engin.
Thanks a lot.
Great talk.
Thanks.